Thanks very much. It's wonderful to be here, even virtually. And today I want to talk to you about distributed tracing in Swift. I want to take you on a bit of a journey and show how we implemented tracing in Swift applications on the server and how some of the upcoming changes in Swift are going to make tracing and server-side Swift development really, really good and really, really fun. So quick introduction. As mentioned, I run a company called Broken Hands, and we do server-side Swift training and consultancy stuff. I'm part of the Vapor core team, and Vapor is a web framework for writing APIs and backends and web applications in Swift. I also sit on the SSWG, which is the Swift server workgroup, and we're responsible for pushing Swift and the interests of Swift on the server with the Swift language. So we have members from Apple and Amazon and MongoDB and Vapor, and we meet every couple of weeks as a steering group to try and influence the language and make working with Swift on the server a great experience. I'm the server-side Swift team lead at raywendlick.com. So it's a tutorial site. And so we have lots of tutorials and books and videos on server-side Swift on there. And as mentioned, I organize server-side.swift, which is a conference on server-side Swift. And I run a number of meetups as well, both in here in the UK and around the world. So I'm completely unbiased when it comes to server-side Swift, as you can tell. But we should have a great talk anyway. And you can follow me on Twitter and Discord and Slack and GitHub as 0xTim. So most of the conferences where I talk, I'm talking to mobile developers who will know what Swift is, but they won't necessarily know that it can be used for the server applications. But I suspect many people here won't have really heard of Swift at all. So Swift is a language that was developed by Apple and released in 2014. Its aim for them was to replace Objective-C as the language of choice for writing applications for Apple platforms. But Swift has kind of grander ambitions, and its aim is to be a language that can be used anywhere and everywhere. And as part of this push, it was open sourced in 2016. So at the start of 2016, it was open sourced and tool chains and runtimes were released for a number of platforms. And these days it supports Ubuntu, CentOS, Amazon Linux, and even Windows. And it's designed to be like a modern language. It's designed to kind of join the cohort of new languages that we're seeing come out alongside the likes of like Go and Rust and Kotlin. And Swift has a number of really kind of cool benefits. So it has some really, really fantastic language features. It's borrowed and tweaked and taken features and concepts from other languages and learned from kind of mistakes of the past. So it has things like optionals, it has generics, it has protocols, and it makes it a really great language to write in. But it also has like a really easy learning curve, so it's really easy to get going. Swift also has fantastic language interop. So it has first-class support for interrupting with C code. So if you need to put in a C library, you can call that natively. There's also Python kit for talking to Python. You can talk to Objective-C, and there's ongoing work at the moment to make interacting with C++ seamless without needing any shims. And Swift is designed to be a really, really safe language. One of its kind of key benefits and aims is to be a safe modern language. And so in practice, this means it has great features for ensuring the safety of your application. So I mentioned it has optionals, and these are effectively nullability checks at a compiler level. And so if you write your code properly, and it's quite difficult not to, things like null pointer exceptions just are a thing of the past. They don't happen. And runtime crashes are exceedingly rare because Swift is strongly typed and statically typed, which means that kind of whole swathes of errors that you get in other languages just aren't possible, which makes it a really, really safe language. And Swift is also really, really performant. So Swift has a fantastic memory model, and it uses automatic reference counting for memory management, which means that you don't have to worry about managing your own memory. And there's no garbage collector, so you can have predictable performance on how your application is going to perform, because there's no garbage collector that's going to kick in at some point in the future. And so you know how it's going to perform. And it also has a really, really low memory footprint. So a typical server-side Swift application is in the region of kind of tens of megabytes for a server application. And you compare this to kind of some of the other languages like JavaScript and PHP, and we're talking orders of magnitude less memory required to run the same kind of code. And many of my clients run on Fargate, on ECS, or on Amazon, AWS, and we can't actually get small enough instances for memory for the kind of tasks that we need. We generally tend to sit at like 5 or 6% of memory usage of the container. So it's a really, really performant language when it comes to memory, but it's also a really performant language when it comes to CPU usage. So Swift is a compiled language. So it compiles down to native machine code. So there's no JVM or interpreter running, which means that you can get really, really high performant code written in a really nice language that's safe. And kind of Swift is kind of joining these modern languages, as I said, but it kind of fills a nice gap. So if you look at some of the modern languages that we have these days, you have Rust. And Rust is a fantastic language that's really picking up traction, especially in like the systems programming world. And it's being used to write operating systems, and it's even making its way into the Linux kernel. But it has quite a complex memory model, and you have to manually manage your memory, and has a really steep learning curve. On the other hand, you have something like Go, which is fantastically simple. It has a fantastic concurrency model and a really easy language to learn, but it's almost too simple in some aspects. It doesn't have things like generics yet. So you end up finding that you duplicate a lot of your code just to write kind of main normal programs. And there's this kind of happy middle ground somewhere with this gap. And I'm not the first person to kind of point this out. There are plenty of people, and I see this quite regularly on Twitter, of people saying there's this like gap between the two that is ripe for a language to come in and disrupt. And in my completely unbiased opinion, I believe Swift is that language. It has a really great features. It's easy to learn and has really powerful features when you need them. So let's talk about tracing. So to give you a bit of a background, I'll talk about tracing, implementing tracing in one of the client projects I've worked on. So the project is a grocery store in New York, and when the pandemic hit, they realized they needed some kind of online presence. The only online presence they had was a simple store with like a PDF that you could download of some of the products they had in stock. And they had a contact form that you could fill in to place an order to go and pick up. And obviously this isn't a great experience. So we built them an online store with an iOS app and a website where customers could browse, view their products. They could see past orders, they could make purchases. And we also had a dashboard where store managers could go in and they could manage inventory and put sales on and see orders, manage customers, etc. And we also built a app for the staff members who go around picking the orders for customers. So previously they'd have to walk around with a printout of an email or a contact form and go and find someone when someone's written 2 packs of cookies and work out what are the cookies they wanted and try and make it kind of the right decision. And so we've built them this app, and they can walk around, scan products and see which products they need to pick from different departments. And it's made their life a lot easier. So this was launched at the end of last year, December last year. And it went down really well. Customers are really pleased with it, and they have a much better experience for ordering online, and staff members are really pleased with it as well. It makes them much more productive. We've seen picking times go down from an average about 45 minutes per order to less than 10 minutes. So staff members are kind of 4.5 times more productive, which is great. So when we were kind of talking to see what's next, like what we're going to do now, we've kind of shipped this great product. We came up with a number of kind of new features. So the first was to be able to support other stores. So Southdown Marketplace, which is the grocery store, isn't just one store. There are a couple of stores around New York, and we wanted to be able to support them all. We wanted to enable things like delivery, so that customers could have their orders delivered directly to them rather than having to go and pick them up. And as we were talking, we kind of realized we've built a really strong platform or strong service. So why not just let other grocery stores come on board and use this? So we've done that. So we've launched MyWebAll, which is kind of ramping up at the moment. And it's basically a service where any grocery store in the US can sign up. We can ingest their inventory, and they get a website for free. They get an iOS app they can use, and they pay a monthly service fee. And it's all done for them without having to do anything. So as part of this, we're kind of adding more and more features. So we need to add things like store customization. So the website is basically generated on the fly. So it's the same app and the same code running underneath the hood, but we have kind of customization hooks so that we can like change the logo, change the title, change the color branding, etc. And we need to make sure that data is separated, because we can't have potentially rival stores viewing each other's sales data. So we're building a quite complex multi-tenant application. And then we wanted more features on top of this. So we want to bring in some of the payment processing in-house so that we can expand to more payment processors. And we also want to do things like integrating with point of sales terminals, so that we can have a single app and single API that manages inventory and manages products and sales and orders and stuff like that. And so we're adding all of these features and more complexity. And when you're building any large application, complexity is inevitable. There's nothing you can do about it. It's just up to you to decide how you're going to deal with that complexity. And I'm not going to go into any of the kind of details or different architectures you can use, but for us, we chose microservices because it allowed us to split up our code and isolate parts of the system and make them a lot simpler, and also reuse code for different potential products and services. But we went into it with open eyes. We knew that choosing microservices has its trade-offs, and we knew that we kind of had to do a lot, because you can't just go and choose microservices. There are considerations that you need to take into account. And the main one, especially for us, was observability and monitoring. And so how do we debug problems across our distributed systems? So with debugging and monitoring on microservices and distributed services, there are three main things that you really care about. The first is logs. And for us, this is fine because we automatically ingest all the logs from the containers into CloudWatch and AWS. So that's not a problem. The second is metrics. And again, that's not a problem because Vapor automatically emits metrics that can be consumed by kind of any backend that conforms to an interface. So we could emit to Prometheus and use Grafana for our metrics. But the third is tracing. And tracing presented a kind of unique opportunity or challenge for us to implement, because tracing in Swift wasn't really a thing and no one else had done it. So for those of you who don't know what tracing is, I'll give a quick overview. Basically, in a distributed system, when you have a request come in, it hits maybe an API gateway or a kind of top-level API, and that will make a request to a downstream service. So in our case, a request to the order service, and the order service will make requests to two different services, say the user service and the item service. And then finally, the item service needs to make a request to the store service, and that's to get all the information it needs to return a response to this request. But what do you do if you have an error? How do you kind of track down this error and work out where it is? So you might have to go through the logs and view all the different logs of the different systems to find out what's going on. And this is quite painful, frankly, and it takes up a lot of time and it's difficult to kind of aggregate everything. So the idea with distributed tracing is exactly the same, apart from when you get a request come in, you create a trace ID for that request. And so that trace ID is then passed down to downstream services so that you can see each trace, where each of the systems it's hit, and find out exactly where it's gone wrong. And that makes it really simple and easy to find your problems and debug issues. So as I mentioned, tracing in Swift provided us a kind of a unique opportunity. And as we're building our application, Swift released the Swift Distributed Tracing library. And this is an API package for packages and libraries to implement and use so that it provides a consistent API for any package to implement tracing without caring about what kind of backend tracing is going to. So each package or library that you use or depend on can use this interface, and then the application can choose which backend to emit the traces to, whether that's Jaeger or OpenTelemetry or X-Ray, for instance, it doesn't matter. So for us to implement this, we had to do three different parts. We had to implement it in three different places in our application, and we had to fork three different libraries. So the first one is the AsyncHTTPClient. So this is an HTTP client library that's kind of foundational to Swift on the server. So lots and lots of packages and libraries use it, and it's designed for sending requests to third-party APIs. And obviously, when you're writing distributed systems and microservices, you use this a lot. The second is Vapor. So Vapor is the web framework that we use and all our services are built on. And so we had to fork it to implement tracing so that it works when incoming requests come in. And the final one was Soto. So Soto is a third-party SDK for working with the AWS API. It basically uses the same specs as all of the other first-party APIs, first-party SDKs, and implements every single API that AWS offers. So whether that's talking to DynamoDB or EC2 or SES or SNS, it has a way of doing that. So to implement this in AsyncHTTPClient, there are a number of steps you need to take. So this is some code that we currently have for doing this. And when a request comes in, or when a request is about to be sent, we create a span. And that span gets a number of attributes like the URL and the HTTP method. And then we execute the request. And when the response comes back, we record the response, like the status code, and then we end the span and we can return the task. And then the important part with distributed tracing is making sure that downstream services know about that trace. So with the HTTP client, what we need to do is inject the headers or inject the span attributes into the headers so that downstream services can see this and see the trace ID and see any of the attributes to make sure that downstream services know that this is part of a trace. Otherwise, it wouldn't work. So this is the really important part. And the next part was implementing it in Vapor. So Vapor, again, is very simple. We create a span when a request comes into the API or the server. We set a number of attributes like the HTTP version, the method, the URL, the host name, et cetera, And then what we do is we hand off the request to a request handler. And when that request handler comes back, we set a number of other attributes on the span. So it could be the status code, the response body, or the response body length, whether it errored or not, how long it took, and then that's our span. And then we can emit that to our tracing systems, and that contains our trace. And the final part was implementing it in Soto. And again, it follows a very similar pattern. When we're about to make a request, we create a span, and these are all child spans of the parent spans that are kind of up ahead in upstream. We set a number of attributes, and some of these are required by X-Ray, which is Amazon's tracing system, such as like the database name, or it could be the service name, and then we pass that on. So in order for us to instrument our code, we have to be able to make sure that those spans are passed down to subsequent requests and downstream services. So a request handler like this, which is Vapor code in Swift, where we make a request to an external API. So in order to instrument this with tracing, what we have to do is pass a context through to the request, and that's how tracing is linked up. And this is very similar to things like Go, where you pass a context around. And that's how we did it. And we implemented tracing, and it went really well. It worked fantastically for us for tracing down bugs. You can see that here's a trace from our test environment where we're getting all of the information about a particular order. We can see which services it hit. We can see how long each service took to respond. We can see the database that it hit. We can see the database table and the request that it actually made to the database. And we can see how long each took. So we hunted down some really kind of horrible performance bugs on certain requests using tracing, because you can see that, for instance, one database call took 900 milliseconds to return. So we can optimize that particular database call and make sure that our requests all work, rather than just seeing that this particular request and have to manually find out why it's taking so long. And here's another example of a request failure. So we can see here that we're making a request to get a particular item for a store. And we can see that it hit the API was fine. It then hit the store service was fine. And then it hit the item service. And DynamoDB, which is our database, returned a correct happy response. So it returned a 200 OK, but the service failed, which means that we couldn't find the item in the database, or the item wasn't in the data that was returned from the database. And that enables us to track down this error really, really quickly. So this is how we've implemented tracing in Swift up till this point. And it's worked really well, and we've been really happy with it. However, there are some changes coming to Swift and that have recently been introduced to Swift that are going to make tracing and server application development really, really powerful. So over the last few couple of years, or year and a half or so, Swift has been busy building up a concurrency model. So up till very, very recently, Swift had no concurrency model, really, no kind of first-class concurrency model anyway. And so in Swift 5.5, which was released in September, it introduced a number of concurrency concepts that we can use. And this is kind of going to take Swift to the next level of server development because it makes things really simple. And one of these is things like async await. So we use async await. And here is an example of some code that we had before async await was a thing. So before async await was a thing, in our code, when we're writing asynchronous requests or asynchronous code, we have to do everything with callbacks. And you can see it's pretty gnarly because we have several places where we return something. We're kind of in a pyramid of doom because we have to kind of nest each callback. So with async await, this just becomes really, really simple, and the number of lines get cut in half. And it makes the code a lot easier to read. So Swift, as part of kind of how Swift works with async await, it needs a way of modeling asynchronous work. And in Swift, this is a task. So a task in Swift is a kind of self-contained piece of work that's going to run asynchronously. It's not a thread. It's not a thread local, and it doesn't have any of the issues that you would see with threads and unsetting them and setting them, etc. And as part of tasks, Swift has also introduced a thing called task local values. Now, task local values are a way of setting properties onto a task that can then be read by downstream child tasks. So one of the main use cases for task local values is distributed tracing. So we can set span IDs and trace IDs in a parent task, and then subsequent tasks can read that span ID and trace ID and attributes without having to do anything. And this solves a number of problems. So if we go back to the code where our callback-based code looked, you can see that in order to instrument this code for tracing, we had to pass a context and pass a context and pass a context and a context and a context. At every point where we're making either database calls or API calls, we have to pass this context. And this is what Go does. And this is problematic because it pollutes your code, and it also relies on the fact that the programmer has to remember to pass that context, because they might not, and they might forget, or they might pass something else. And you're also reliant on the library that you're using, or packages you're using, making sure that they handle that context correctly and don't override anything. And this is a problem that you see in Java quite a lot, because Java has a real problem with unsetting context because there's no structured way to do this. So you have to manually do this when you exit the async scope. And this causes issues even with things like logging with the request ID, because you have to make sure as a library developer that you don't overwrite anyone else's thread local data. And as an application developer, you're hoping that library developers do this, and there's no structured way of doing it. So this isn't even possible. This kind of error isn't possible in task locals by design. So in a task local, you can set your data in a task, but nothing else can write it in child tasks. Child tasks can read it, but they can't override it. And it's it's type safe as well. So this kind of wipes out all these kind of different errors that we see with tracing and thread local issues, thread local data in other languages. So with task local values, in order to instrument our code to make sure that the task local values are passed to child tasks, we have to rewrite it to this. And yeah, there's nothing to do. It's done automatically for you by the compiler. You don't have to pass it anywhere. As soon as you set it on a task, it's available for downstream tasks to read. And it makes it really, really powerful, because this wipes out all these errors of forgetting to pass it, making sure things are consistent. So in order to set task local values, they're quite simple. You can define a task local value. So in this case, we're setting a table name for a database. And then we just set that with the task local syntax, as you can see here. And it's asynchronous as well, because it might be set somewhere in a task that's already doing something. And then we can send our request, and we don't have to pass it anywhere because that task local value is set. And then in our application code, so this could be in the Soto where we're kind of making that request, we can read that information out. And again, it's type safe, and you can have nested objects if you want. So if you want to nest your span data, you can do. And it's very easy to read, and it works really, really well. So you don't have to worry about it. It's not like stringly typed. It's really simple to read. So this is one of a number of features in Swift that are making server-side development really powerful and asynchronous code really powerful. So Swift has also introduced the concept of actors. There's a thing called sendable, which is a way of marking your data as thread safe. And this is enforced by the compiler, so that your code has to be thread safe. So thread safe and data access issues, again, become a thing of the past. It's another class of errors that Swift are wiping out by using the compiler and type safety to ensure that things are safe. So actors is a way of the actor model Swift has introduced recently. So it lines up with things like sendable to make sure that accessing data across different tasks in an asynchronous environment is safe and works really well. So if you haven't already checked out Conrad's talk from yesterday, I highly recommend you do. Conrad talked about how to do distributed systems with Swift. And as part of that, announced Swift's introduction of distributed actors. So this is a way of doing cross-process or cross-service requests and kind of synchronization and data synchronization that's type safe, enforced at a compiler level. So first class support for doing cross-service, cross-process data access. It's extremely powerful. It's very difficult to kind of comprehend. But again, it just shows how far Swift's coming for use as a systems and server language. So that's all I have. Thank you very much. I hope you've enjoyed the talk, and I hope you've enjoyed listening about how we're using Swift on the back end. And I believe we have some questions now. So I think I jump into the spatial chat thing, or can I do them here?
Yeah, we still have a little time. So if you want to, do you have, actually I had a question, but I'm going to ask the question from Discord first, which is, oh yeah, now we're getting 3 questions. Good times. All right. So since you're part of the server-side working group, or SSWG anyway, do you have any update on the various efforts to make Swift less reliant on external libraries? The reason why they're asking has to do with Docker images remaining relatively heavy for a compiled language, especially compared to like Rust.
Swift's main problem at the moment is linking with libicu for doing things like UTF-8 strings and stuff like that, and dates and stuff. There is ongoing work to make this less reliant. It's a long-term piece. So we're talking years, and even the dog is sad about it. But if you compile your Swift application in a Docker container, you can actually compile it as a statically link, or statically link the Swift runtime at least. And your Docker images go down to about 100 megabytes. So they're pretty small if you strip out all the tool chain and stuff. But they're not kind of like micro small. One day, hopefully. But yeah, it's an ongoing piece of work that will take a number of years.
Cool. And one question that I had just quickly is about sendable. Does that mean like immutable or synchronously accessed or what?
It's asynchronously accessed. So if you want to change the data, you have to go through basically a asynchronous access pattern. So you use the await keyword because something else might be accessing it. So that's how actors work, and it enforces that thread safety.
So it sort of like wraps an object in like a lockbox or something like that.
Yeah, but it's a very lightweight lock, and the kind of the compiler enforces the fact that you can't lock yourself or create a deadlock. So that's done by done by the compiler, rather than you having to make sure you're not deadlocking yourself.
Right, great. And so the final question actually is just for you to share any links to the Discord room about anything that they can use to know more about this topic. So
yeah, absolutely. I'll put a load of links into the Swift forums and Swift server work group and Vapor and stuff like that. Definitely.
Awesome, great. Well, thank you very much for taking the time to chat with us. I really appreciate it. And this was a really interesting presentation for me, especially not being so familiar with Swift. And I know that this distributed tracing is something that we use at work and is really valuable for a lot of people. So I appreciate you taking the time to talk to us about this topic.
Cool. I'll go hang out in the spatial chat place as well if everyone has any other questions.
Yep.